In today's lecture, we are going to see the calculation of two very important parameters which are used in the discussion of crystal structure. And these two parameters are atomic radius and packing fraction. But our discussion will be limited for the calculation of these two parameters because in this lecture you will find how we can calculate the atomic radius and packing fraction only of cubic crystal. So our discussion is limited only to cubic crystals for the calculation of atomic radius and packing fraction. Actually, these two parameters are very useful, very important parameters for the discussion of a structure of crystal lattice. Okay. So before knowing how we can calculate these two parameters in case of the cubic crystal lattice, first of all we will define these two parameters. So let us see how we can define the atomic radius. When you say atomic radius, what does it mean? Actually, if you have to find the atomic radius, you have to think about the nearest neighbors of a crystal lattice. So if let us consider these are the two nearest lattice points in the crystal lattice, and these two nearest neighbors are separated by a distance x, then half of this distance x, which is the nearest neighbor separation, that is called atomic radius. So I have written here, you can see, if x is the distance between nearest neighbors, then atomic radius, which is denoted by the symbol r, is equal to x by 2. So whenever we will have to find the expression for the atomic radius of a crystal lattice, first of all we have to see which are the nearest neighbors and how much they are separated. Once you know the separation between the nearest neighbor, you have only to divide that separation by 2 and you will get the atomic radius. So this is a very simple concept, simple definition. Okay. Now, what is this packing fraction? Actually, packing fraction is defined as the total volume of atoms in a unit cell are divided by the volume of the unit cell. Okay, it means you have to find what is the total volume of atoms in a unit cell, and then you have to divide that volume of atoms in a unit cell by the volume of the unit cell. Then you will get the packing fraction. And for this, let us consider that this n represents the number of atoms in a unit cell. Okay, and this small v, I have assumed it is the volume of each atom, because volume of each atom will be same, and that I have assumed is small v. And this capital V represents the volume of the unit cell. Now let us see. I have defined the packing fraction as total volume of atoms. Total volume of atoms in a unit cell are divided by volume of the unit cell. Okay, this is the definition of the packing fraction F. Okay. Now, as you have assumed that the total number of atoms in a unit cell is n and each atom has a volume V. So what will be the total volume of atoms? Since volume of one atom is a small v, therefore volume of n atoms will be simply n into v. This is the total volume of atoms in a unit cell. So packing fraction F will be defined by n times v divided by capital V, where capital V represents the volume of the unit cell. Now, as I have told you earlier that the calculation of these two parameters will be done in this lecture only for cubic crystals. So we will think about the cubic crystal only. As you know, in case of a cubic crystal, what is the total number of atoms in a unit cell? You have already learnt in the previous lecture this fact. You know, in case of a cubic crystal, the total number of atoms in a unit cell is found by this formula. N equal to Ni plus Nf divided by 2 plus Nc divided by 8. This is the formula for finding the total number of atoms in a unit cell in case of cubic crystal. Mark this formula is only for cubic crystal. Okay. You know, you have already studied that Ni here represents the number of interior atoms or body-centered atoms. Nf represents the number of face-centered atoms and Nc represents the number of corner atoms. Okay. So using this very formula, we will always find the total number of atoms in a unit cell in case of cubic crystal. Okay. And then we have to find what will be the value of this small v, which represents the volume of an atom. As you know, atoms are spherical, so the volume of each atom, which I have denoted by the symbol small v, that will be equal to 4 by 3 pi r cube, where r is the radius of the atom. Okay? And how radius will be calculated, you have already learned. Now you know, the volume of a unit cell in general is given by this formula. This is actually the modulus of A dot B cross C. But here, in case of cubic crystal, you know, A is equal to B and that is equal to C. So this the unit cell of a cubic crystal is simply a cube, and so after simplification this volume will be simply a cube because you know the volume of a cube is simply cube of the edge. So using these three facts, we will be able to find the packing fraction because we will substitute all these values in this equation 1 and then we will get actually the packing fraction of the crystal lattice. Okay. So this is the basic definition, basic concept of atomic radius and packing fraction. Now we are going to see how we can calculate these two parameters in case of the cubic crystal. As I have told you earlier, and you know already, that a cubic crystal has actually three types of unit cell: simple cubic, which is also called primitive, and face-centered and base-centered, face-centered and body-centered. So in all these three cases, we will calculate these two parameters. Okay. Actually here in this equation 2, I have substituted 4 by 3 pi r cube at the place of a small v and a cube at the place of capital V. So this is the formula from which we will calculate the packing fraction for a cubic crystal. Okay. Now let us see the case of simple cubic or primitive cubic. Okay. Actually, I have not shown the complete unit cell, that is the complete cube here. This is just a simplified figure from which we can easily calculate the radius of the atomic radius and the packing fraction of the lattice. Actually, I have shown only one of the faces of the cube because in this case the atoms are only at the corners, not at the center of any face or not at the center of the body of the unit cell. So in this case, the nearest neighbors are simply the atoms situated at the corners of adjacent corners of a face. So you can see that if A is the lattice constant, then the nearest neighbor, which I am marking here, this 1 and 2 or 1 and 3 or 1 or 2 and 4, these are the nearest neighbors and they are separated simply by a distance a. So in this case, the nearest neighbor separation x is equal to a. And you have learnt that the atomic radius is simply equal to half of the separation between the nearest neighbors. That is, r is equal to x by 2. But since in this case x will be equal to a, so atomic radius will be simply a by 2. Okay. This is the atomic radius of the simple cubic lattice. Okay. So I have written it here. You can see that if a is the lattice constant, then in this case nearest neighbor distance is equal, x is equal to a, and so the atomic radius will be simply a by 2. Now we will calculate the packing fraction of the simple cubic lattice. As you know, for calculating the packing fraction, you have to know what is the number of atoms in a unit cell. And for that, you use the formula n is equal to ni plus nf divided by 2 plus nc divided by 8. Okay. As in this case, you know, in case of simple cubic lattice, the lattice points are only at the corners. Okay. So at the place of ni, which represents the number of lattice point inside the at the center of the lattice, that will be actually equal to 0. So this is 0, and there is no lattice point even at the center of the faces. So nf is also 0. So second term will be 0. But there are lattice points at all the 8 corners. So nc is 8. So this is 8 over 8, and so n is equal to 1. And this calculation you have already seen in the previous lecture. Okay. Now we will substitute the value of this n and the volume of the one atom and volume of the unit cell in this formula 2, which is the formula for calculating the packing fraction. So after substituting this value, you can see f will be equal to what? Since n is 1, so at the place of n I have written 1 and 4 by 3 pi r cube. But you can see r in this case is a by 2. So this is a by 2 whole cube and divided by a cube. Okay. And after simplification, you can see this a cube will cancel out and our result will be f equal to pi over 6, which is equal to 0.52. You will see among all the 3 unit cells, the packing fraction in this case will be least. We will see later on that the packing fraction in case of face-centered and base-centered lattice, actually that will be greater than this 0.52. So packing fraction of the simple cubic lattice is least. Okay, and this is 0.52. I will suggest you must remember this value, because in objective question it is directly asked to you that what is the packing fraction of a simple cubic lattice. So if you remember this data, you can easily answer the objective questions. Okay. Now we will see the same calculation in case of face-centered cubic lattice, that is FCC. Okay. Again, I have not shown the complete unit cell here, and thus only a simplified figure has been shown so that we can easily understand the calculation of these two parameters. I have shown here only one face of the cube, which is ABCD. And you know, in case of face-centered cubic lattice, there are lattice point at these corners A, B, C, D, and also at the center of this face, which is O. This is also a lattice point. Actually, from you can see I have shown here 5 dotted spheres. These actually represent the atoms at the corners and at the center of the face. Okay. Now, the distance between A and B, you know, this is equal to lattice constant A, and similarly the distance between B and C, that is length of this side BC, is also equal to A if the lattice constant is A. Okay. Now see the figure. This AE represents the radius of the atom at the corner A. Similarly, this CF also represents the radius R of the atom at the corner C. Okay. And this EO and OF represents the radius of the atom at the center of this space. So you can see in this case, actually the radius R can be calculated in a very simple manner. You can see the geometry of the figure. If you want to know what is the length of this face diagonal AC, you can easily say that this will be AE plus EO plus OF plus FC, and all these are R. So this AC will be equal to what? This will be R plus R plus R plus R, that is 4R. So the length of the diagonal of this face is equal to 4R. But this diagonal can be also found by using the Pythagoras theorem, and you can see that AC square will be equal to AB square plus BC square. Okay. But AC you have calculated, this is 4R, so this is 4R square, and AB and BC both are A, so these are A square plus A square. And after simplifying it, you can get the value of R. I have written it here. You can see that AC, as I have told you, is equal to this AE plus EO plus OF plus FC, and this is equal to 4R. Okay. And AC square, this is AB square plus BC square. So 4R square is equal to 2A square. And so that you can write R square equal to 2A square over 16, that is A square over 8. And so R will be equal to A over 2 root 2. So this is the atomic radius in case of the face-centered cubic lattice. I think this is a very simple calculation and you have clearly understand it. Now, after knowing the expression for the radius in case of face-centered cubic lattice, now we will see what will be the packing fraction for this. And you know, for getting the value of packing fraction, first of all we will calculate N, which is the number of atoms contained in the units in this unit cell. And for this, you know the formula. This is Ni plus Nf by 2 plus Nc over 8. But in this case, you know, Ni is 0 because there is no lattice point at the center of the body of the lattice. Okay. But Nf is 6 because at the cube has 6 faces and at the center of each face there is a lattice point. So this is 6 over 2 plus 8 over 8, that is equal to 4. So in this case, the number of atoms contained in a unit cell is equal to 4. So now use the formula for getting the packing fraction. You know this is F equal to N times 4 by 3 pi R cube divided by A cube. Now we will substitute the value of R. You have obtained that R is equal to A over 2 root 2. And n you have obtained just now, this is equal to 4 in this case. So f will be equal to 4 times 4 by 3 pi times a over 2 root 2 whole cube and divided by a cube. After simplification, you can see that f will be equal to pi over 3 root 2, which is equal to 0.74. This is actually the packing fraction for the face-centered cubic lattice. And you will see this is the highest value or the largest value of packing fraction in case of cubic crystal. Okay, as you have seen that in this case the packing fraction is 0.52 and in this case you have obtained this is 0.74. Okay. Now finally we are going to see the same calculation for the body centered cubic, that is BCC lattice. So again in this case we will calculate first of all the atomic radius, and I have shown here the complete cube. And you can see for the finding the nearest neighbor separation, you can think about an atom at the corner A and diagonally opposite corner G. Okay, and this atom has been shown by the dotted sphere, you can see. And at this O is the center of the cube, and here there is also a lattice point, you know. And this bigger dotted sphere represents the atom situated at this center. So you can see the figure. This AK is the radius of the atom situated at corner A, and similarly this GL is the radius of the atom situated at the corner G, and OK and OL, these are the radii of the atom situated at the center of the cube. Okay. So again from the geometry of figure it is obvious, it is clear that if you want to know the length of the diagonal, body diagonal of this cube, that is AG, that will be equal to what? That will be equal to AK plus KO. But AK is R, KO is also R, plus OL, and OL is also R, plus LG, which is also R. So this is also equal to 4R. So the length of the diagonal of this unit cell is equal to 4R. Okay. I have written it here, you can see. So AG is equal to 4R. Okay. Now you know that if we write the vector AG, what will be this vector AG? Using the polygon law of vector addition, you can write this AG will be equal to vector AB plus BC plus CG. You know the polygon law of addition of vectors. Now if you assume that AB is along x-axis, BC is along y-axis and CG is along z-axis, because the three edges of a cube are mutually perpendicular. So this will be simply equal to AI plus AJ plus AK. Okay. And so if you want to find the square of the modulus of AG, what will be this? This will be A square plus A square plus A square. That is 3A square. Okay. But you know modulus of AG is 4R. So you can write 4R whole square is equal to 3A square. And from here you can easily find what will be R. Okay. So in this way, we can calculate the radius. I have written it here, you can see for your convenience, that AG is equal to AI plus AJ plus AK, and mod of AG square is equal to 3A square, but mod of AG is 4R, so 4R whole square is equal to 3A square, and R square will be 3A square over 16, and therefore the atomic radius R of BCC lattice, this will be root over 3 by 4 times A. This is the atomic radius of the BCC lattice. Okay. Now after getting the expression for the radius of BCC lattice, you can easily find the packing fraction for it. Again, we will find the total number of atoms in this unit cell, and using the same formula, that is n equal to Ni plus Nm by 6 plus Nc by 8. In this case, you know, there is a lattice point inside, at the center of the cube. So Ni in this case is equal to 1, but there is no lattice point at the center of the face. So Nf is 0, so second term will be 0. And again, at each 8 corners, there is a lattice point. So Nc is 8. So this will be equal to 2. Okay. So in this case, N is equal to 2. Now we will use the formula for F. You know, N is equal to, F is equal to N times 4 by 3 pi R cube divided by A cube. Okay. But you have obtained that in this case N is equal to 2. So this is 2 times 4 by 3 pi R cube. But you have obtained that R in this case is root 3 by 4 into A. So this will be root 3 by 4A whole cube. And after simplification, you will get that this is equal to root 3 pi divided by 8. And this will 0.68. So you can see that this packing fraction is less than the packing fraction of the FCC lattice. As you have seen, it is equal to 0.74. So after getting the values of packing fraction of all these 3 unit cells of a cubic lattice, we conclude that the packing fraction in case of the FCC lattice is highest, and in case of simple cubic or the primitive cubic cubic lattice is least. Okay. So the face centered lattice is the most dense. Here the density of the atoms is highest. Okay. I think this was a very simple concept, but it is very useful in discussing the structure of a crystal. So we have definitely understood clearly each and every step, as I hope. Thank you very much.